Hi, everybody. Today, I want to talk about a subject that's pretty near and dear to my heart, and that is the transition from big data to real-time data, and doing so at massive scale. My name is Denis Coady. I'm a product manager at Molecular. As a company, we're really focused on unlocking the power of real-time analytics and AI for customers. And we do it with a low latency database product of our own. So before I start going into a new format and how the benefits of it, let's first talk about what does real-time really actually look like. I think everybody can have an idea in their own head, but for the sake of simplicity, I like these four attributes. First off, low latency of your queries. Real-time doesn't matter if it takes forever to get answers out of your data set or your database. When you're running these queries, if the data is stale by the time it becomes available to your queries, it's dramatically less valuable to you. So, decreasing the processing time is going to help that freshness, and that's ultimately going to make the queries and the insights way more valuable. Throughput, and I'm not talking about like bandwidth or what have you, but can you get the data from your upstream sources into your database fast enough? If you can't, you're going to see back pressure, and ultimately the freshness quickly decreases. Concurrency. We don't live in an era where we're serving one or two users or applications anymore. We're quickly going to an era with machine learning models, with high-powered analytical applications, and direct to consumers. And so because of that, we have to start thinking not in terms of ones and twos, but hundreds and thousands. So your current architecture, you may not think it's real time. Well, it might not be, and here might be a few reasons why it's not. Starting with just getting data into the database. You're probably having trouble getting your data in fast enough. Now, there's a lot of technologies out there on the market now, and there's a lot of easy to use ones like Kafka, for instance, that can quickly help alleviate these problems. But even if you do, even if you're getting your data in fast enough, you're now really facing a really tough choice. Do you pay the price of performance at query time with high latencies and slow queries, or do you pre-aggregate and create denormalized tables ahead of time in a batch process? Well, that will help speed up your queries, but you're just shifting the cost preemptively, and so now your freshness is quickly diminishing. So after you make that trade-off between slow queries or stale data, now you have to try to figure out, how can I start serving hundreds or thousands of users? Typically systems start to suffer from real performance degradation and concurrency problems around 100 users. That's potentially fine for now, but in the future, it actually will become a huge bottleneck. So one of the ways you can solve it is just buy more hardware, and you can just throw a lot of money at the issue. That's fine for the short term, but long term, what you're going to notice is there's sort of a death spiral of buying more hardware, which requires more people to maintain that hardware, which is going to require more overhead and oversight. And quickly, you're going to notice your entire initiative is getting bogged down and very frustrating and very slow to change. Well, if you don't want to go down necessarily that route, there's some other compromises and trade-offs you can do. Like I said prior, you can pre-aggregate your data, and now you're sacrificing freshness for low latency queries. You can pull your records ahead of time, whether in Kafka or other tools, and increase the batch size, which will help with your throughput. But once again, it's going to suffer in your freshness. you can throttle your resources. So, instead of having every query try to take up your entire CPU resource, you can make the query slower and serve more customers at the same time. So you're sacrificing latency for concurrency. And if you're not ready to make any trade-offs, you can just throw a lot more money at the problem. And it's a temporary band-aid, but ultimately you're really not helping the problem. You're just kicking the can down the road. So, what happens when you don't want to make trade-offs? Well, you got to start thinking a little bit deeper about where the root of the problem is. And this company was built out of a philosophy that the root of the problem is the way we format and store and process data. So why? Whenever you're inventing a new technology in something like as saturated as the data market, why build something new? Is it just not built here? Or is it because of a real need that's not being served? So Molecular was actually born out of the latter. There was nothing on the market that could help a prior startup that it was born out of deal with their data problem. So they had trillions of data points and billions of users, and they were performing customer segmentation for events on this data to try to help better understand the audience. Now, the problem is for a startup, it required a lot of machines, and there's a lot of maintenance overhead and data management. That was really a nightmare. That wasn't the root of the business. The business was delivering, results. It wasn't about maintaining servers. And unfortunately, only a single customer request could actually be delivered at a time. So, there was challenges with scaling. And so because of that, some engineers at the company, at the prior startup, realized, well, this feature-oriented way of thinking could really help alleviate a lot of the problems. Now, when you're thinking about going to a new format, I think it's always worthwhile to look at the evolution of data formats to see why certain decisions were made and what the trade-offs are. The original format is row-oriented. And so this is kind of what we think a table looks like. You have rows and columns. And when you're trying to answer analytical queries, what you'll find is that it's only a few columns you actually care about. You don't typically care about the entire table. So with our eyes, we scan down the columns we care about, and in our heads, we'll think about it. But the challenge is that's not how data is laid out on disk, and that's not how it's processed by computers. It's always processed in a very linear format, left to right, and then you go to the next row. And the problem is for disks, this is really inefficient to try to filter out data. There's a lot of seeks, little bits of actual reading of data, and then you have to go find that next bit of data on the disk. And what you're gonna notice is that, unfortunately, in some cases, the most performant way to do that is to read the entire table. And that's horrific. What's the point of only wanting to filter on a few columns if you have to read the entire table anyways? So in comes column-oriented. What's nice about column-oriented is by transposing rows and columns, we can dramatically reduce, how much data is actually being read. You put the seek exactly where the column starts, you read the column, and you're done. You don't read the entire table. And so because of that, it's far less data that you have to filter out to begin with. The data is typically more homogeneous, so you're going to get really good compression rates, typically, I think 75% plus. And so that's where a lot of the performance increases came from. Your parquets and other formats. Not bad, but a feature-oriented can do better. So here's an example of a columnar format. And what I'm going to show you is when we change it into a feature-oriented format, where the real benefits lie. So when you look at a column format, here's an example of one with a bunch of hardware by hardware manufacturers in certain years. If I only care about Juniper equipment, all I really have to do is first filter out on manufacturers which rows are Juniper. Now that sounds good, but the challenge is I still have to read all of that data and then filter out which rows actually matter. In this particular tiny table, not a problem. But in a big data system, when you have billions or trillions of records, that can still be a considerable amount of data. And then you got to store results and go back and filter again. So what makes feature-oriented formats better? Well, a feature-oriented format actually extracts out that value uniquely. So the value is only ever stored once. And in its place is a binary bit. That's it. And that is used to denote whether or not this feature is present in a record. And so right away, I hope it starts to become a little bit more clear as to why feature-oriented formats dramatically will reduce how much data you're actually reading and processing. Because instead of hoping for the best with compression, where it will never get to as good as a bit, you can dramatically, orders of magnitude, reduce how much data you're actually processing, and do so in a way that's far more friendly to a computer. Computers don't know human languages. They know ones and zeros. So in this particular case, we can show all routers or switches manufactured by Juniper in 2017. Well, what does that mean? That means all I really have to do is start looking at which rows have a router feature, a switch feature, and then in manufacturers, what is a Juniper feature, and in 2017. And from there, I can do some computer native Boolean operations to very quickly and efficiently calculate what my final result set is. Now, I put a lot of weight on the size of data being reduced. And the reason is that the performance characteristics of a system for data management is typically going to be denoted by how much data it has to store and process. If you have to use a lot of memory, which is in bytes, that's going to cause you to have to dramatically increase the size of your system. If you have to transmit a lot of data, then you're going to have throughput issues. If you have to store and read a lot of data from disks, then you're going to have slow reads and slow queries. So even CPU usage, which we typically think of in terms of time, is really a function of how much data and how many steps it has to do. And so in a slightly clever way, we can think about that even in terms of bytes. So when you start thinking about and start working with a feature-oriented format, you get some pretty cool results that have to do with the LFT and C of the real-time story. You're going to get low latencies because you can now structure data in a way that minimizes how much data you're reading and writing to disk, which will dramatically increase the performance of your queries. Also, because it's binary, it actually plays extremely well with CPU and caching algorithms. You're not jumping around to different files, so the caching is a little bit more predictable, so you're not going to have as many cache misses. And the CPU can use native instructions like ands and ors to do your filtering. You'll notice that because you can store a lot more data, you can have massive tables. We're pretty familiar with millions of features and trillions of records. So you don't need to worry about sparseness. You don't need to worry about having to do joins. You can focus on landing your data in a feature-oriented format and being able to do an analytics on it directly from there. When you so one of the steps of a feature-oriented format is you got to actually extract the feature extraction. What's really cool, you don't actually have to do that in a centralized location. What we actually do with a lot of folks is preemptively do feature extraction at the source before it ever hits the network. And so that allows us to distribute the workload. So however you want to use it, whether it's with Kubernetes or elastic systems of some kind, you can distribute that workload however you want. And then by the time it hits the wire, it's in a feature-oriented format that's super compressed to the binary. So you're transmitting a lot less data. That's how you're going to get that high throughput. What's also nice too is the actual values, the features. We can now decouple that, right? And so you can compress that, analyze it, transmit it, store it in a completely different location, however you want. So because it's binary, it plays itself really well with atomic operations. And so that's going to allow some pretty nifty tricks you can do for improving both your concurrent read and writes. But also, because it's so much smaller, we can fit a lot more in memory, and you can then serve a lot more queries concurrently, because by being feature oriented, you are making every query more efficient, so you can inherently serve more at the same time. So I'm about to share some real world results, and that's because this is what we do. We're a feature oriented database, and we can show some pretty cool, pretty impressive results. Millisecond querying, instantaneous fresh data, massive cost reductions, and a greater than 10x data compression. So I can stand up here and talk about the benefits all day, but what are some real world results? What can we actually expect, right? One of our customers who adopted a feature oriented mindset is a global video ad tech company. Before, with a more traditional architecture, they had 24 to 72 hour delays before they could target audiences, because they had a very batch-oriented architecture. And so they had to wait for all the batch processing to be done, which is very inefficient. When they moved to features, they're now able to do real-time processing, and do so with significantly less hardware. So they went from about 1,000 machines to 10. And by the way, with those 10 machines, they're ingesting 1 million records per second and serving 1,000 customers. So pretty massive numbers, simply by changing the way they thought about how they store and process data. A great customer of ours that we've been partnering with for a long time is Q2. They help financial institutions target and message their customers to help make sure that they can get value out of all the products available. Previously, they used a mix of big data and traditional RDBMS systems, which, once again, a lot of batch processing. I think that that's a pretty common situation, especially with preaggregation. Once again, by moving to a feature mindset, their new architecture allows for real-time updates, about an order of magnitude less hardware, and they can still do updates to 5 billion attributes on 50 million records in real time. So they can make dramatic changes to their database and not have to wait. This is going to be perfect for an MLAI use case. Last but not least, we have a customer who does energy price prediction. So they are predicting energy pricing by monitoring tens of thousands of nodes on the electrical grid in Texas, public and private data, financial market data, and doing a huge fusion effort to try to predict what the pricing is going to be. They could predictably figure out about 14 days ahead of time the pricing, but the predictions included 48 hours old data due to pre-aggregation. So, anytime you're trying to predict, time is kind of the enemy, and losing, 1/7 of your prediction just to wait for pre-aggregations is kind of painful. When they adopt features, they can move away from days old data to real-time data. They can layer in a lot more data sets, which is going to give them a lot better insights and predictions. And they're doing so with trillions of records, and they're ingesting about 3.5 billion records every day. So with that, I'm here and happy to answer any questions you may have. Any questions I don't get to, feel free to email me. I will answer as soon as I can, and I'm always happy to engage with folks interested in being a feature-oriented mindset. So thank you very much.